On August 6, 2025, the James Webb Space Telescope turned its infrared eyes towards something unprecedented, a visitor from another star. Not just any visitor, the third confirmed interstellar object ever detected, and the strangest by far. Its chemistry defied expectations. Its speed shattered records. And buried in Webb's data was a signature that made astronomers rewrite their assumptions about how planetary systems form across the galaxy. 3 anomalies emerged that night, each contradicting what we thought possible. First, this comet contained a carbon dioxide to water ratio of 16:1, 16 times more carbon dioxide than water, a ratio never seen in any solar system comet at this distance. Not just unusual, unprecedented. Second, it was racing through space at 68 kilometers per second. That makes it the fastest interstellar object we've ever observed. To put this in perspective, it's faster than 99% of stars moving through the Milky Way. Only objects ejected from the most violent stellar encounters reach these velocities. Third, ESA's Gaia telescope traced its path backward through time, across 4.27 million years of interstellar drift, and found something unsettling. It didn't come from anywhere nearby. No star in our neighborhood could have ejected it with enough force to reach these speeds. Instead, the data pointed somewhere far more intriguing and far more ancient. A boundary zone where the oldest stars in the Milky Way meet the youngest, a region that formed over 10 billion years ago. If the analysis holds, this icy traveler predates our sun by 5 billion years. It witnessed the galaxy's infancy, and it carries chemical fingerprints from a world we may never see. But here's what has researchers at NASA, ESA, and observatories worldwide on edge. Its behavior doesn't match any known comet class. Not from here, not from there. It's something else entirely. So what exactly is Comet 3I Atlas? How did we discover it? What did each telescope reveal as more observatories joined the hunt? And why are 3 competing formation models failing to fully explain its chemistry? In the next 10 minutes, we'll trace this object's journey from a faint point of light in Chile to the most scrutinized interstellar visitor in history. We'll explore what its alien chemistry tells us about distant planetary systems. We'll examine 3 competing hypotheses struggling to account for every piece of data, and we'll reveal what upcoming observations scheduled for late October 2025 might finally solve the puzzle. Let's begin with the night everything changed. July 1st, 2025, an observatory in Chile, the Atlas telescope, specifically designed to scan the sky for Earth-threatening asteroids, detected something unusual. A faint point of light, located 4.5 astronomical units from the Sun, roughly Jupiter's distance, but its motion was wrong, too fast, too angled. Within hours, telescopes in Hawaii, Arizona, and Chile converged on the target. They revealed a faint coma, a halo of gas and dust surrounding the object. This was no inert rock, it was actively outgassing, releasing frozen material into space. Then came the breakthrough. Astronomers dug through archival data from previous years, searching for earlier accidental captures. The Zwicky Transient Facility had photographed the object in mid-June. Atlas itself had unknowingly recorded it weeks earlier. With these pre-discovery sightings, researchers traced a longer orbital arc across the sky and calculated something astonishing: the object's orbital eccentricity, 6.1. For perspective, solar system comets have eccentricities below 1. An eccentricity of 6.1 is equivalent to firing a bullet through a wind tunnel. The sun barely curves its path. This comet wasn't bound to our star at all. It was on a one-way journey through the solar system, moving at speeds that could only mean one thing: it came from beyond. On July 2nd, it received its official designation, 3I Atlas, the third confirmed interstellar object in human history, after 1 Oumuamua in 2017 and 2I Comet Borisov in 2019. According to NASA's Transiting Exoplanet Survey satellite, the comet was already active at 6.4 astronomical units, far beyond the distance where water ice normally sublimates. This meant something more volatile was fueling it: carbon monoxide, carbon dioxide, ices that vaporize in conditions too cold for water. This was the first clue that 3I Atlas wasn't formed in our solar system. Its behavior hinted at an exotic chemistry shaped in the cold, distant reaches of a completely different star system. But here's where the standard models broke down. By July 4th, the Very Large Telescope in Chile captured spectroscopic data. Two discoveries emerged. First, the object's interstellar origin was confirmed with high precision. Its motion, speed, and trajectory left no doubt. Second, traces of atomic nickel and cyanide gas appeared in its coma, elements commonly found in solar system comets. This suggested something profound. Comets from other planetary systems may share similar building blocks with ours. The ingredients for life might be common across the galaxy, but there's a problem. Nickel and cyanide typically form in water-rich environments during comet formation, not in CO2-dominated regimes. We were seeing chemistry that shouldn't coexist. Then the Gemini North Telescope in Hawaii captured multicolor images across visible and infrared wavelengths. The data showed noticeable color shifts, not just from different filters, but from changes in the comet's own physical behavior. Gas emissions surged. Cyanide, nickel, the same exotic compounds detected earlier, growing in intensity as the comet approached the sun. On July 21st, Hubble Space Telescope locked onto the target. Three major findings emerged from a single observation. First, size constraints. Hubble's high-resolution images estimated the solid nucleus, the core beneath the gas, at approximately 1.2 kilometers in diameter, though possibly as large as 5.6 kilometers. That makes it comparable to most solar system comets. Based on this size estimate, 3I Atlas has a minimum mass of approximately 33 billion tons. To put this in perspective, that's 1,000 to 1 million times more massive than 1I Oumuamua, which was estimated at roughly 5.5 billion tons, or 2I Comet Borisov, estimated at 30 to 40 billion tons. This makes 3I Atlas the largest interstellar visitor we've ever observed with precision. Second, Hubble revealed a visible plume of dust being actively ejected, direct evidence the comet was strongly outgassing, releasing frozen material as it warmed from 6.4 AU to closer distances. Third, its incredible speed, 68 kilometers per second relative to the Sun, aligned with models suggesting it had drifted through interstellar space for billions of years, shaped by countless gravitational encounters with stars, gas clouds, and perhaps unseen planets in distant systems. But the data revealed an unexpected pattern when James Webb turned its infrared instruments toward the comet on August 6th. August 6th, at 3 astronomical units from the Sun, roughly 3 times Earth's distance, temperatures should theoretically be high enough for water ice to sublimate. Most solar system comets at this distance show bright, water-rich comas, but 3I Atlas didn't follow the script. Webb's infrared spectrometers detected a carbon dioxide to water ratio of 16 to 1. To place this in context, this is equivalent to finding an iceberg made almost entirely of dry ice instead of frozen water. The typical carbon dioxide to water ratio in solar system comets at 3 AU is roughly 1 to 5. Webb found 16 to 1. That's a reversal of proportions more than 80 times larger than the norm. This challenges core assumptions in planetary formation theory. 3 competing models emerged in peer-reviewed literature within weeks of Webb's data release. The first model, proposed by the Webb Initial Analysis Team and published in Rapid Communications to the Astrophysical Journal in late August, suggests 3I Atlas formed in a planetary system where the host star blew away water vapor early in the protoplanetary disk phase. If water was depleted during the first million years of system formation, stripped away by intense stellar radiation before comets could coalesce in the outer icy regions, the remaining composition would be dominated by carbon dioxide ice instead. This model explains the CO2 dominance perfectly, but it has a critical problem. Ground-based spectroscopy detected nickel and cyanide in the coma. These elements typically form in water-rich environments, where water molecules react with silicate rocks and metals. If the system was water depleted, how did nickel and cyanide form at all? The model works for CO2. It fails for the water-forming elements we're actually detecting. The second hypothesis comes from dynamical simulations, published by ESA's Planetary Science Division. It argues 3i Atlas passed close to another star during its interstellar journey, a flyby, at perhaps 100 astronomical units from a hot young star, could have stripped surface water ice through intense radiation and stellar wind. The remaining carbon dioxide, buried deeper and more protected, would survive. The water-forming elements detected today could be from a thin water ice layer that remained shielded beneath the CO2 crust. But this model has its own contradiction. If the water was stripped millions of years ago during the stellar encounter, what's driving the comet to be actively outgassing now? Thermal models predict that a comet this small, stripped of surface water, should be dormant at 3 AU. Yet Webb detects active outgassing consistent with current vaporization of volatile ices. The timeline doesn't fit. The physics doesn't align. The third possibility emerged from thermal modeling teams at Caltech and the University of Arizona. Water may still be buried deep beneath the comet's crust, insulated from sunlight, and harder for Webb's instruments to detect through the carbon dioxide veil. Perhaps the water didn't sublimate at 6.4 AU because it was protected in subsurface layers. Only carbon dioxide, more volatile and more accessible, reaches the surface, creating the 16:1 ratio we observe. But here's the problem. Such thermal shielding would require an unusually thick CO2 crust at this distance and outgassing level. Thermal models suggest the heat penetrating the comet would break through such shielding. The insulation wouldn't hold up under current conditions. None of these models fully explains the combination of extreme speed, unusual chemistry, active outgassing at unexpected distance, and the coexistence of water-forming elements with CO2 dominance. Then ESA's Gaia telescope provided the most intriguing clue yet. Using Gaia's billion-star catalog map, researchers traced 3i Atlas backward through time, simulating its journey across 4.27 million years. They identified 62 stars it may have passed within potentially significant gravitational influence. The surprise, none had strong enough gravitational pull to significantly alter its course. The comet didn't originate anywhere near our solar neighborhood. Instead, the trajectory analysis pointed to a more distant birthplace, the boundary between the Milky Way's thin disk and thick disk. This is a transitional region where the youngest metal-rich stars of the thin disk, formed in the last few billion years, meet the ancient metal-poor stars of the thick disk. The thick disk formed over 10 billion years ago during the early Milky Way's violent assembly. If 3i Atlas truly came from this zone, it could be a relic from the early galaxy, possibly over 10 billion years old, making it twice as old as our Sun. One emerging hypothesis from teams studying galactic dynamics suggests this represents a new class of interstellar object, ancient comets ejected during the Milky Way's chaotic youth, when stellar encounters were far more frequent and violent than today. The physics mirrors what we see in dense star-forming regions. Globular clusters and other high-density environments routinely fling objects into interstellar space at extreme velocities through gravitational interactions. What if 3i Atlas preserves primordial chemistry from the first billion years after the Big Bang, shaped by conditions radically different from the modern galaxy? Theoretical work by teams at MIT and Cambridge studying early galaxy dynamics predicts such objects should exist. But this is our first potential detection. The carbon dioxide dominance might not reflect a specific planetary system's chemistry, but rather the cold, radiation-poor environment of the ancient Milky Way's outer regions, where water vapor never condensed efficiently in the first place. But the question remains, what ejected 3i Atlas with such force that it's been traveling for billions of years at 68 kilometers per second? Three competing ejection mechanisms remain unresolved. First, planetary scattering. If 3i Atlas formed in a binary star system and one star passed through a dense stellar cluster, gravitational interactions could have flung bound planets and comets outward at extreme velocities. Simulations suggest this happens in perhaps 1 to 3% of systems in crowded regions. Second, supernova shockwave. If a massive star in 3I Atlas's birth cluster went supernova, the shockwave could have accelerated the comet to 68 kilometers per second. This mechanism is more violent, but also rare, requiring the comet to survive the blast, which itself is unusual. Third, tidal disruption in a binary. If 3I Atlas orbited too close to a binary star pair, periodic gravitational squeezing could have driven differentiation, carbon dioxide settling in deeper layers, while water remained surface-locked, only to be stripped later by radiation. This physics operates at scales rarely tested in laboratories, but analogs exist in Jupiter's moon Io, where tidal heating produces extreme volcanism and compositional layering. None of these mechanisms fully accounts for why the comet retained structural integrity while being accelerated so violently. The observations challenge every model we've built. We began with a faint point of light in Chile. Within weeks, it became the most scrutinized interstellar visitor in history. Atlas detected it, Hubble measured it, Webb decoded its chemistry, Gaia traced its origins. Each observation added precision and revealed deeper mystery. The data journey revealed 4 key insights. Its chemistry points to formation environments radically different from our solar system. Its speed and trajectory suggest a violent ejection billions of years ago. Its ancient origin implies we're witnessing a time capsule from the early galaxy itself. And its behavior contradicts every formation and composition model we currently possess. What we know with certainty: 3I Atlas is real, measured, and chemically anomalous. Its CO2 to water ratio is 16 to 1. Its speed is 68 kilometers per second. Its origin trajectory points to regions over 10 billion years old. What remains theoretical, whether it's truly from the ancient Milky Way, what ejected it, and why its chemistry violates our assumptions about comet formation. What we expect to learn in the next 6 weeks: high-resolution spectroscopy, scheduled for late October 2025. Using Keck Observatory's adaptive optic systems, we'll measure isotopic ratios in carbon-12 versus carbon-13, nitrogen-14 versus nitrogen-15, and deuterium versus hydrogen in 3I Atlas's coma. These ratios act as fingerprints, distinguishing between different formation environments. An ancient comet from the early galaxy would show isotopic ratios different from solar system objects. A recently ejected comet would match modern stellar neighborhoods. According to NASA's Interstellar Object Working Group, these isotopic measurements will definitively discriminate between the 3 competing formation models. If carbon-13 is enriched, it suggests formation in an older, more processed region. If deuterium is depleted, it suggests stripping by stellar radiation. If neither shows anomalies, we're missing something fundamental about how this object formed. The answer arrives in 6 weeks. ESA's Gaia mission continues tracking stellar positions with unprecedented precision. NASA's upcoming Nancy Grace Roman Space Telescope, launching in 2027, will survey wide fields with infrared sensitivity, specifically designed to detect more interstellar objects and test whether 3I Atlas represents a statistical anomaly or the first member of a new population. Early projections suggest Roman could identify 10 to 20 interstellar objects per year. If 3I Atlas's unusual chemistry becomes common in that sample, we'll know that our models of planetary formation are incomplete. If it remains an outlier, we'll need to explain a 1 in a million event. 3I Atlas will exit our solar system by late December 2025, fading beyond detection. But its brief visit has forever expanded our perspective, reminding us we're part of a much larger cosmic story still unfolding across the stars. NASA's Roman Space Telescope launches in 2027 with infrared capabilities specifically designed to detect more interstellar visitors. Early projections suggest it could identify 10 to 20 objects per year, building the first statistical sample of their chemistry, speed distributions, and origin points. Subscribe to track these discoveries as they come in. Be the first to know when isotopic ratios resolve the ancient comet hypothesis. See whether 3I Atlas's unusual chemistry represents an outlier or a glimpse into the galaxy's ancient past. The final observations happen in 6 weeks. This is the window to understand what this comet is. After December 2025, it's gone. In Cosmos, we trust.